Newton's laws of motion. There's three laws of motion. The first is known as Newton's first law, and this states that an object at rest will remain at rest forever unless acted upon by a net external force. Newton's second law gives the relationship between net force, mass, and acceleration. The acceleration of an object is given by the net force over the mass of the object. That's Newton's second law. Now let's just go back to Newton's first law. If the acceleration is zero, then the net force has to be zero. Right, so this is the condition for static equilibrium or dynamic equilibrium. So for example, an airplane flying with a constant speed in a straight line has a net force on it of zero. So if you add it up all the forces, the thrust, the drag, the lift, and the weight of the plane, you would get zero. The third law states that for every action there's an equal and opposite reaction. But what exactly does that mean? Well, here's an equation that I like to use for Newton's third law. If there's a force on object A due to object B, then there's a force on object B due to A, where FAB is equal to the negative of FBA. Okay, so you have two forces. Notice that they act on different objects. Also notice that they're exactly equal but oppositely directed. They occur simultaneously. So which you call the action and which you call the reaction is arbitrary. Let's take a look at an example. Okay, so here's a person standing on the ground. Let's take a look at the forces acting on him. Well, the most obvious force of them all, of course, is the person's weight. And that is balanced by the normal force, okay, which is an electric force, and it acts perpendicular to the surface, and it's exerted on this person by the floor. But notice that these two forces act on the same object. So they cannot be the action-reaction pair that is described in Newton's third law. So what are the action-reaction pairs? Well, let's take a look at the weight. What exactly is the weight? The weight is a force of gravity, and it's the force on this person due to the earth, right? Because there's a gravitational force of attraction between any two masses. So this person's mass is gravitationally attracted to the Earth's mass. So from Newton's third law, doesn't there have to be a force acting upward on the Earth, which we show acting at the center of mass? So this will be the force on the Earth due to the person, which has the same magnitude as the person's weight, which is the force on the person due to the earth. So these two forces are an action-reaction pair. The normal force is the force on the person due to the ground upon which he is standing. So isn't the reaction force then the force on the ground due to the person? And these two are electric forces. Now let me show you something. Suppose the floor gives way. Well, then the person is going to be in a state of free fall. So what forces act on him? Well, he still has weight. That's why he's falling. Okay, so we have the weight, and we still have the reaction force, if we call that the action. Remember, it's arbitrary what you call the action and what you call the reaction. So you still have the force on the earth due to the person, which is equal to the magnitude of the weight, which is the force on the person due to the earth. So you still have those two forces. But since the floor is gone, you don't have a normal force, and hence you don't have the force on the ground due to the person. So you see, I think most people would think that these two forces are the action-reaction pairs that are described in Newton's third law. But you see what happens is if you get rid of the floor, the normal force disappears. So, but you still have the weight. But you can't have a lone force according to Newton's third law, right? There has to be these equal and oppositely directed forces that act on different objects, right? For every action, there's an equal and opposite reaction. Okay, so these two can't be an action-reaction pair. Now, let's take a look at this person accelerating. The person's accelerating because the weight is a net force. But doesn't the Earth also have to accelerate? Because isn't the force on the Earth due to the person, which is the reaction to the force on the person due to the Earth, a net force? So the Earth is going to accelerate upward. But won't it be a tiny bit? Because if you look at Newton's second law, the mass of the Earth is huge. You have this force on the Earth due to the person. And then we have the same force on the person due to the Earth, but oppositely directed, and that's divided by a little mass. So this huge mass of the Earth going into the force on the Earth due to the person is going to result in a very tiny acceleration. Whereas this tiny mass going into the same force, magnitude, is going to give you a larger acceleration, and this is what we call the acceleration due to gravity. So both the Earth and the person accelerate toward each other. They accelerate toward a common center of mass. But the Earth undergoes a much smaller acceleration than the person. Let's take a look at another Newton's second law example. Okay, suppose we have a person riding an elevator. Okay, so here's a person in the elevator. Now, what forces are acting on this person in the elevator? Well, one of the forces, of course, is the person's weight. The other force would be the normal force. Now, the size of the normal force could be either greater than the weight, less than the weight, or equal to the weight. It would be equal to the weight if the elevator is not accelerating. So the sum of the forces on the person would be 0. If the elevator is accelerating upward, then wouldn't the normal force have to be greater than the weight? Which would mean that the person feels heavier than he normally feels. So let's apply Newton's second law to this. We have sigma F equals ma. So the net force equals the mass of the person times the person's acceleration. We're going to call up positive. So we have the normal force minus the person's weight equals the mass of the person times the acceleration of the elevator. Solving for Fn, can you see that the person is going to feel heavier than what he normally feels? You can see that from this. By the way, what if the elevator is accelerating downward? Well, if you go through this again, you would see that the person feels lighter than they normally feel. What if the person is in free fall because the cable snapped? Well, then if you solve for Fn, the acceleration of the elevator is going to be g. And since up is positive, I can take the vector symbol off of g and introduce the direction. So there you have weight minus mg, but weight from Newton's second law is mg. So we get mg minus mg equals 0. By the way, why is the weight of something found by taking mass times the acceleration due to gravity? Okay, the reason this works is as follows. Newton's second law states that the net force is equal to the mass times the acceleration. So if I want to figure out the weight of a 1 kilogram mass, what I do is I imagine it falling, and when it's falling, isn't the net force its weight? And isn't accelerating at g, 9.81 meters per second squared near the surface of the Earth. So the weight of a 1 kilogram mass then, using Newton's second law, is just its mass times the acceleration due to gravity. So you're not converting between mass and weight.